If space had a beginning, why hasn't it stopped growing? What is the universe expanding into? And why? Every second, the universe grows larger. But what's fueling it? Is space stretching? Or is reality itself unraveling? What if the farther we look, the faster space escapes us? To understand why space is growing, we first have to ask what space really is. Let's begin. Have you ever wondered what happens in the darkness between stars? As you gaze at the night sky, something remarkable is happening that our eyes cannot see. You cannot hear it. You cannot feel it. But right now, space is stretching. Every galaxy, every star, every silence between them is growing. Not because they are moving through space, but because space itself is growing. It has always grown. It is still growing. And tonight we drift into the question, why does space keep getting bigger? When we look at distant galaxies through our most powerful telescopes, we see them drifting away from us. Not because they are fleeing, but because the cosmos itself is expanding. Like raisins in rising bread dough, galaxies move apart as the space between them stretches. This cosmic expansion happens everywhere, at every moment, silently reshaping our universe. It is perhaps the most profound discovery in modern astronomy. The universe is not static. It breathes. It grows. It has been expanding since the very beginning, since the moment everything we know flashed into existence. The night sky above you is different than it was yesterday. The stars have moved slightly farther apart. The galaxies have drifted a bit more distant. Not by any amount you could notice in a human lifetime, but over billions of years, this gentle stretching transforms the cosmos completely. Imagine standing on a beach, watching the tides slowly rise. The water does not move in one direction, rushing past you. Instead, it swells everywhere at once, lifting every shell, every grain of sand. This is how space expands, not with a direction, but everywhere, carrying all things with it. The light from the stars travels across this expanding ocean of space. Some rays have journeyed for billions of years, from galaxies so distant that they appear to us as they were when the universe was young. In the time since that light began its journey, those same galaxies have moved even farther away, carried by the silent tide of cosmic expansion. When we look deep into space, we are also looking back in time. The light from distant galaxies has traveled for millions, even billions of years to reach us. In that time, space itself has continued to expand. Some galaxies are now so far away that their light will never reach us, carried away by the relentless stretching of space. This expansion shapes everything we see and everything we are. It determines how galaxies form, how stars live and die, and ultimately, how long the universe as we know it will exist. It tells us about our cosmic past and hints at our cosmic future. The story begins with a moment of creation, the Big Bang, which was not an explosion in space, but the beginning of space itself. From that first instant, space has been growing, cooling, and evolving. The expansion carries within it the echo of that beginning, a whisper we can still detect in the cosmic microwave background radiation that fills the universe. But why does it expand? What force drives this cosmic growth? Is it simply the momentum from that initial creation? Or is there something more mysterious at work, a dark energy that pushes space apart? And what does it mean for us, tiny observers on a small planet, to live in a universe that keeps getting bigger? How does cosmic expansion shape our understanding of our place in the cosmos? What does it tell us about the ultimate fate of everything we know? As you rest beneath the night sky, know that you are part of this grand cosmic story. The atoms in your body were forged in stars that existed in a smaller, younger universe. You exist in a moment of cosmic time when the universe is neither too dense nor too diffuse, when stars still shine and galaxies still form. In ancient times, our ancestors believed the heavens were fixed, unchanging, eternal. The stars were points of light embedded in crystal spheres that rotated around Earth. But now we know the truth is far more wondrous. The universe is dynamic. It changes, it grows. The night sky you see tonight is not the same as the one your great-grandparents saw, nor will it be the same as the one your great-grandchildren will see. This expansion is imperceptibly slow by human standards. If you could somehow mark 2 points in empty space 1,000,000 light-years apart and wait a year, they would move apart by only about 70,000 kilometers. Yet over cosmic time, this gentle stretching accumulates. Galaxies that were once neighbors drift apart. Clusters of galaxies spread out. The universe becomes less dense, cooler, darker. There is a haunting beauty in this cosmic expansion. It means that every moment in the universe is unique. The cosmos of yesterday is gone forever. The cosmos of tomorrow will never be exactly like today. We exist in a singular moment in cosmic history, a universe of a particular size, a particular temperature, a particular arrangement of matter and energy. Our journey tonight takes us from the first moments after the Big Bang to the far distant future, trillions of years from now. We will explore not just how space stretches, but why, and what it means to live inside a cosmos that never stops growing. So close your eyes and imagine the vastness above you. Feel the quiet wonder of a universe in motion, where every point moves away from every other point, where space itself keeps getting bigger, carrying us all on a journey without end. As you drift towards sleep, let your mind expand with the cosmos, stretching beyond the boundaries of everyday thought into the infinite possibilities of an ever-growing universe. As we begin our journey into the expanding universe, we first need to understand what we mean when we say space is expanding. It is one of the most counterintuitive concepts in all of science, yet it forms the foundation of our modern understanding of the cosmos. When we say that space expands, we do not mean that galaxies are simply moving away from each other through space, like ships sailing across an ocean. Rather, the ocean itself is growing larger. Space, the very fabric of reality, is stretching. This is fundamentally different from ordinary motion. Imagine a loaf of bread dough with raisins scattered throughout. As the dough rises, each raisin moves away from every other raisin, but the raisins themselves are not moving through the dough. They remain fixed in their positions. It is the dough expanding between them that carries them apart. This is how galaxies move apart in our expanding universe. Another way to visualize this is to imagine a balloon with dots drawn on its surface. As you inflate the balloon, each dot moves away from every other dot. From the perspective of any single dot, all other dots appear to be moving away. The farther a dot is from the one you are observing from, the faster it appears to recede. This is precisely what we observe in our universe. Distant galaxies move away from us faster than nearby ones. But this balloon analogy has its limits. Our universe is not expanding into anything. There is no space outside the universe into which it grows. When we say the universe expands, we mean that distances within the universe are increasing. The space between galaxies stretches, but the space within galaxies, solar systems, planets, and people does not noticeably expand. This is because the gravitational forces that bind these structures together are strong enough to overcome the expansion of space. Think of it this way. If you were to place 2 markers on a rubber sheet 1 centimeter apart, and then stretch the sheet to twice its size, the markers would now be 2 centimeters apart. You did not move the markers. The sheet expanded. Now imagine that the rubber sheet is 3-dimensional and infinite in all directions. This is closer to how space expands. In our universe, this expansion follows a remarkable pattern discovered by Edwin Hubble in the 1920s. The speed at which galaxies move away from us is proportional to their distance. A galaxy twice as far away moves twice as fast, 3 times as far, 3 times as fast. This relationship, known as Hubble's law, is a direct consequence of the expansion of space itself. But what exactly is space? We tend to think of it as nothingness, the absence of things. But to a physicist, space is something real. It has properties. It can bend in the presence of mass and energy, as Einstein's theory of general relativity tells us. And as we now know, it can stretch and grow. Space is not just the stage upon which cosmic events unfold. It is an active participant in those events. When massive objects like stars and black holes warp space around them, they create what we experience as gravity. And when space expands, it carries galaxies along with it in a cosmic dance that has continued for nearly 14 billion years. The expansion of space affects not just the positions of galaxies, but light itself. As light travels across expanding space, its wavelength stretches too. This is called cosmological redshift, and it is different from the familiar Doppler effect that causes the sound of a passing ambulance to change pitch. Cosmological redshift happens not because the light source is moving through space, but because space itself expands as the light journeys through it. Imagine drawing a series of waves on our rubber sheet, then stretching the sheet. The waves would stretch too, becoming longer. This is what happens to light in expanding space. The longer the light travels, the more space expands during its journey, and the more its wavelength stretches. This is why light from the most distant galaxies is shifted far into the red end of the spectrum, sometimes even into invisible infrared wavelengths. This stretching of light tells us something profound. The universe we see today looks different than it did billions of years ago. The early universe was smaller, denser, hotter. Galaxies were closer together. There was less empty space between them. Over time, as space expanded, the universe cooled and thinned out, allowing atoms to form, stars to ignite, galaxies to take shape, and eventually life to emerge. In this way, the expansion of space has shaped our cosmic history. Without it, the universe would remain an infinitely hot, dense soup of particles. Stars would never form. Chemistry would never happen. We would not exist. There is a quiet poetry in this cosmic stretching. Every point in the universe gently moves away from every other point, not in any particular direction through space, but with space itself. There is no center to this expansion, no special place from which everything recedes. From any galaxy in the universe, all other galaxies would appear to be moving away, just as we observe from our own Milky Way. This universal expansion transforms our understanding of cosmic geography. In a static universe, we might ask, where is the edge? Where is the center? But in an expanding universe, these questions change meaning. There is no edge to space itself, no boundary beyond which there is something else. And every point can be considered the center of expansion. Because expansion happens everywhere, the expansion of space also transforms our understanding of cosmic time. The universe has a history, an evolution from earlier, denser states to later, more diffuse ones. This gives time an arrow, a direction. The future is more expanded than the past. The universe grows older as it grows larger. As you drift towards sleep, consider the remarkable nature of the space around you. It is not simply emptiness. It is a dynamic, growing thing, carrying the light of distant stars across billions of years to reach your eyes. The same cosmic expansion that moves galaxies apart has helped create the conditions for you to exist, to breathe, to dream beneath the night sky of an ever-growing universe. When we think about the beginning of our universe, we often imagine a tremendous explosion, a bang that scattered matter across empty space. But this common image is deeply misleading. The Big Bang was not an explosion in space. It was the beginning of space itself. Roughly 13.8 billion years ago, the universe as we know it began. But it did not begin as a point in pre-existing space. Rather, all of space, all of time, all of matter and energy were compressed into an infinitesimally small, infinitely dense, infinitely hot state. There was no outside to this initial state, no empty space into which it could explode. The Big Bang was not matter expanding into empty space, but space itself beginning to expand, carrying the fundamental ingredients of our universe with it. This moment of creation remains veiled in mystery. Our current theories of physics break down when trying to describe the exact beginning. We cannot yet speak with certainty about the first fraction of a second, when the universe was smaller than a subatomic particle and hotter than trillions of degrees. But from that tiny fraction of a second onward, we can trace the story of cosmic expansion with growing confidence. What happened in those earliest moments was unlike anything in our everyday experience. The universe underwent a phase of expansion so rapid and extreme that cosmologists gave it a special name: cosmic inflation. During this inflationary period, space expanded faster than the speed of light. A region smaller than a proton grew to the size of a grapefruit in less time than it takes light to cross an atomic nucleus. This may seem to violate Einstein's rule that nothing can travel faster than light, but that rule applies to the movement of objects through space, not to the expansion of space itself. Space can stretch as fast as the laws of physics allow, and during inflation, it stretched at an almost incomprehensible rate. This primordial growth spurt lasted only a tiny fraction of a second, but it fundamentally shaped our universe. Inflation smoothed out the cosmos, making it remarkably uniform on the largest scales. It also stretched quantum fluctuations, microscopic variations in the density of matter and energy, into the seeds that would eventually grow into galaxies and clusters of galaxies. When inflation ended, the universe continued to expand, but at a much slower rate. The enormous energy that had driven inflation was converted into a hot soup of fundamental particles. This soup was so energetic that not even atoms could form. Instead, particles of matter and antimatter popped in and out of existence, annihilating each other in flashes of pure energy. For reasons we still do not fully understand, matter gained a slight edge over antimatter. For every billion particles of antimatter, there were 1,000,000,001 particles of matter. When the matter and antimatter annihilated each other, that tiny surplus of matter remained. This is the matter that makes up everything we see today, from stars and planets to the cells in your body. As the universe continued to expand, it cooled. By the time it was 1 second old, it had cooled enough for protons and neutrons to form. After about 3 minutes, these protons and neutrons began to combine into the nuclei of the lightest elements: hydrogen, helium, and traces of lithium. But the universe was still too hot for electrons to join these nuclei and form complete atoms. Light could not travel far before being scattered by free electrons. The universe was opaque, like a dense fog. This foggy state continued for about 380,000 years, as space kept expanding and cooling. Finally, when the universe had cooled to about 3,000 degrees Celsius, electrons could combine with nuclei to form the first atoms. Suddenly, light could travel freely through space. This light, released when the first atoms formed, still fills our universe today. We detect it as the cosmic microwave background radiation, a faint glow coming from all directions in the sky. It is the oldest light in the universe, the afterglow of creation itself. With atoms now formed, the universe entered a period sometimes called the Cosmic Dark Ages. Space continued to expand, and the matter within it began to clump together under the force of gravity. Regions that were slightly denser than average pulled in more and more matter. Over millions of years, these growing clumps of matter formed the first stars, bringing light back to the cosmos. The first stars were unlike any that exist today. They were massive, burning hot and bright, but briefly, with lifespans of only a few million years. When they died in tremendous explosions called supernovae, they scattered newly formed elements into space. These elements, heavier than hydrogen and helium, would become the building blocks of planets, and eventually of life itself. As space continued to expand, these first stars gathered into the earliest galaxies. Galaxies clustered together into groups, clusters, and superclusters, creating the vast cosmic web that we observe today. Throughout all of this, space itself kept stretching, carrying galaxies apart from one another. In the earliest epochs, the expansion of the universe was slowing down. The gravitational pull of all the matter in the cosmos was acting as a brake on expansion. For billions of years, it seemed that the fate of the universe might be to expand more and more slowly, perhaps eventually to stop expanding altogether and begin to contract. But about 5 billion years ago, something unexpected happened. The expansion of the universe began to accelerate. After slowing for billions of years, space suddenly began to stretch faster and faster. This acceleration continues today and appears to be driven by a mysterious force that pervades all of space. Astronomers call it dark energy, though we understand little about it beyond its effects on cosmic expansion. Throughout this long history of expansion, from the inflationary epoch to the modern era of accelerating growth, one thing has remained constant. Space itself has been stretching. The universe has never been static. It has always been in motion, always growing, always becoming. When we look at the night sky, we are looking back in time, seeing galaxies as they were millions or billions of years ago, when the universe was significantly smaller than it is today. And as we gaze at these ancient lights, space continues its silent expansion, carrying those same galaxies even farther away. There is something humbling in the realization that we exist within this vast cosmic story. The atoms in our bodies were forged in stars that lived and died in a smaller, younger universe. We breathe the breath of a cosmos that has been growing for nearly 14 billion years. And with every passing moment, the space around us stretches a little more, as the universe continues its ancient pattern of growth and transformation. As our journey through the expanding cosmos comes to a close, we return to where we began, beneath the night sky, gazing up at distant stars and galaxies, all silently drifting away from us as space itself stretches. We have traveled from the first moments after the Big Bang to the far future, trillions of years from now. We have explored not just how space expands, but why, and what it means to live inside a cosmos that never stops growing. Space does not grow loudly. It stretches quietly, slowly, gently. And in that growth, everything changes. Galaxies move apart, light fades, but wonder remains. The universe we observe tonight is not what it was at its birth, nearly 14 billion years ago. It has cooled from an unimaginably hot plasma to a cosmos cool enough for atoms, molecules, stars, planets, and life to exist. It has expanded from a state smaller than a subatomic particle to a vastness that extends at least 93 billion light-years across. The very fabric of reality has stretched, carrying galaxies apart like islands drifting on a cosmic sea. And the universe will never be this way again. Tomorrow, it will be slightly larger. The galaxies will be slightly farther apart. The light from distant stars will be stretched just a bit more. In a trillion years, the night sky will look dramatically different, with most galaxies having disappeared beyond our cosmic horizon, carried away by the relentless expansion of space. This ceaseless transformation reminds us that we exist at a particular moment in cosmic history. We inhabit what might be called a Goldilocks era of cosmic evolution, after the universe cooled enough for complex structures to form, but before it expands so much that new stars can no longer ignite. Our moment is neither too hot nor too cold, neither too dense nor too diffuse. It is just right for complexity, for chemistry, for consciousness. In this way, the expanding universe gives meaning to our existence. We are not merely in the universe, we are of the universe. The atoms in our bodies were forged in stars that could only exist because the universe expanded at just the right rate. The energy that flows through our cells originated in the Big Bang and has been transformed countless times as the cosmos evolved. The oxygen we breathe was created in stellar furnaces and scattered by supernovae in a universe of a particular size and age. The expansion of space shapes not only physical reality but also our understanding of time. In an expanding universe with a beginning, time has a direction, an arrow. The past was different from the present, and the future will be different still. This aligns with our human experience of time as something that flows, that cannot be reversed, that carries us from birth toward death in one direction only. Yet, within this one-way flow of time, the expanding universe offers a kind of immortality, not for individual living things, but for the patterns and information they create. The light from stars long dead still travels through space, carrying information about those stars across billions of years. The elements created in those stars become parts of new stars, new planets, new living things. Even as individual structures decay, the cosmos preserves the influence of what came before. There is a quiet poetry in this endless transformation. The universe does not simply grow bigger, it grows more complex, more structured, more intricate in its patterns of matter and energy. Expansion allows heat to flow, entropy to increase, complexity to emerge. Without the stretching of space, the universe would remain a hot, dense soup of particles, forever unable to cool enough for atoms to form, for chemistry to happen, for life to evolve. The expansion that carries galaxies apart also creates the conditions for your existence. You are, in a very real sense, a child of the expanding universe. Your atoms, your energy, your consciousness exist because space has been stretching for nearly 14 billion years, cooling the cosmos from its hot beginning to its current temperature, just right for liquid water, carbon chemistry, and the emergence of minds capable of wondering about their place in it all. As you rest beneath the night sky, remember that you are not separate from this cosmic unfolding. You are part of it, a brief but conscious expression of a universe becoming aware of itself. The same forces that move galaxies apart flow through you. The same history that shaped the cosmos shaped your body. The same future that awaits the universe awaits all that you are and all that you create. Space does not grow loudly. It stretches quietly, slowly, gently. And in that growth, everything changes. Galaxies move apart. Light fades, but wonder remains. Sleep now in a universe that gets bigger with every breath. You are not lost in it. You are part of its becoming. The cosmos continues its ancient pattern of expansion, carrying stars and galaxies ever farther apart. But it also carries something new: consciousness, curiosity, the capacity to observe and understand this grand unfolding. Through you, the universe observes itself. Through you, the expanding cosmos becomes known. As you drift towards sleep, imagine the vastness stretching all around you. Feel yourself not as a tiny speck in an incomprehensibly large space, but as a conscious node in a cosmic network, connected to all that exists by the same expanding fabric of space-time. You breathe the breath of a growing universe. You think the thoughts of a cosmos becoming conscious. You dream the dreams of a reality that never stops transforming. This is the gift of the expanding universe. Not eternity, but change. Not stasis, but evolution. Not finality, but endless becoming. In a cosmos that grows forever, nothing remains the same, yet nothing is truly lost. All that was continues to influence all that will be, in an unbroken chain of cause and effect, stretching from the Big Bang to the far future, encompassing every star, every planet, every living thing, and every conscious thought. Sleep now in a universe that gets bigger with every breath. You are not lost in it. You are part of its becoming. How can we be so confident that the vast emptiness between stars and galaxies is actually expanding? After all, none of us can see space stretching with our naked eyes. We cannot hear it or feel it. The expansion happens too slowly and on too grand a scale for our human senses to detect. Yet astronomers speak of cosmic expansion with remarkable certainty. What evidence convinced them that space itself is growing? The story begins in the 1920s, at a time when most scientists believed the universe was static and eternal. The prevailing view was that the Milky Way constituted the entire universe, a fixed island of stars in an otherwise empty void. But this understanding was about to be fundamentally transformed. At Mount Wilson Observatory in California, an astronomer named Edwin Hubble was making careful observations of what were then called spiral nebulae, fuzzy patches of light that many astronomers thought were clouds of gas within our own galaxy. Using the 100-inch Hooker telescope, then the largest in the world, Hubble was able to resolve individual stars within these nebulae. Among these stars, Hubble identified Cepheid variables, a special type of star that brightens and dims in a predictable pattern. The period of this pattern is directly related to the star's true brightness, which means that by measuring how bright the star appears to us, we can calculate its distance. This made Cepheid variables invaluable cosmic yardsticks. What Hubble discovered was shocking. These spiral nebulae were not gas clouds within the Milky Way at all. They were separate galaxies, vast collections of stars, far beyond our own. The universe was suddenly much larger than anyone had imagined. But Hubble's next discovery was even more profound. Working with fellow astronomer Milton Hugh Mason, he began measuring the spectra of these distant galaxies, analyzing the light they emitted. When an object moves away from us, the wavelengths of light it emits are stretched, shifting toward the red end of the spectrum. This is known as redshift. Conversely, an object moving toward us produces a blue shift, with wavelengths compressed toward the blue end of the spectrum. Hubble and Humason found that almost all galaxies showed a redshift, indicating they were moving away from us. But the pattern was not random. The farther a galaxy was from Earth, the greater its redshift, the faster it was receding. This relationship, now known as Hubble's law, had a startling implication. The universe was expanding. If galaxies are moving away from each other at speeds proportional to their distances, it suggests they all originated from the same place. Imagine a film of an expanding universe played backward. All galaxies would converge, coming closer and closer together until they reached a single point. This realization led to the concept of the Big Bang, the idea that our universe began as an infinitely dense, hot state and has been expanding ever since. But was there another explanation for the pattern Hubble observed? Could it be that Earth is at the center of some enormous explosion, with galaxies flying away from us in all directions? This would violate the Copernican principle, the idea that Earth does not occupy a special position in the universe. It would mean we are at the exact center of everything, an unlikely coincidence. The expansion of space provides a more elegant explanation. If space itself is stretching, then from any galaxy in the universe, all other galaxies would appear to be moving away. There is no center to the expansion, no special place from which everything recedes. This matches our observations perfectly and aligns with our understanding that Earth does not occupy a privileged position in the cosmos. Further evidence for cosmic expansion came from the discovery of the cosmic microwave background radiation in 1964. Arno Penzias and Robert Wilson, two radio astronomers at Bell Labs in New Jersey, detected a faint microwave signal coming from all directions in the sky. This ubiquitous radiation had been predicted years earlier as a leftover from the hot, dense early universe. As space expanded and cooled, this primordial radiation stretched along with it, shifting from visible light to microwave radiation. The cosmic microwave background provides a snapshot of the universe when it was just 380,000 years old. It shows us that the early universe was remarkably uniform, with only tiny fluctuations in temperature and density. These fluctuations, stretched by cosmic expansion, became the seeds for all the structures we see today, from galaxies to clusters of galaxies to the vast cosmic web. Over the decades, our measurements of cosmic expansion have become increasingly precise. In the late 1990s, two teams of astronomers set out to measure how the expansion of the universe was slowing down over time due to the gravitational pull of matter. To their astonishment, they found the opposite. By observing distant supernovae, explosions of dying stars that shine with predictable brightness, they discovered that the expansion of the universe is accelerating. Space is stretching faster now than it was billions of years ago. This acceleration led to the concept of dark energy, a mysterious force that permeates all of space and drives accelerated expansion. We still do not know what dark energy is, only that it makes up about 68% of the total energy content of the universe and pushes space apart. Another line of evidence comes from the light elements created in the first few minutes after the Big Bang. The theory of cosmic expansion predicts specific amounts of hydrogen, helium, and lithium should have formed during this period of primordial nucleosynthesis. The observed abundances of these elements in the universe match these predictions with remarkable accuracy. The expansion of space also explains why the night sky is dark. In an infinite, eternal, static universe, every line of sight should eventually end on a star, making the night sky as bright as the surface of the Sunday. This is known as Olber's paradox. But in an expanding universe with a finite age, light from the most distant stars has not had time to reach us, and light that is on its way has been stretched and weakened by cosmic expansion. The darkness of night is itself evidence that space is growing. Perhaps the most direct evidence of cosmic expansion comes from observations of objects so distant that the light we see from them was emitted billions of years ago. By looking at galaxies at different distances, we are essentially looking at different epochs in cosmic history. We can directly observe how the universe has evolved over time, confirming that it was indeed smaller and denser. The cumulative weight of all this evidence makes the expansion of space one of the most well-established facts in modern science. From Hubble's initial observations to the precise measurements of space telescopes and microwave detectors, from the abundances of light elements to the accelerating recessions of distant supernovae, multiple lines of investigation all point to the same conclusion: space itself is growing. As you lie beneath the night sky, this invisible expansion unfolds all around you. The space between atoms does not noticeably expand, nor does the space within our solar system or even our galaxy. But the vast gulfs between galaxies stretch incrementally with each passing moment, carrying the light of distant stars on an ever-lengthening journey across an ever-growing cosmos. As we've journeyed through the expanding universe, we've seen how space stretches, carrying galaxies apart like raisins in rising bread. We've explored the Big Bang, not as an explosion in space, but as the beginning of space itself. We've examined the evidence that convinced astronomers the cosmos is growing. Now we turn to perhaps the most mysterious aspect of cosmic expansion. Why is it speeding up? For decades after Hubble's discovery, astronomers assumed the expansion of the universe was gradually slowing down. This made intuitive sense. The gravitational attraction between all matter in the cosmos should act as a cosmic brake, gradually reducing the rate of expansion over billions of years. The universe might expand forever, but more and more slowly, or it might eventually stop expanding and begin to contract, ending in what cosmologists called the Big Crunch. But in 1998, two independent teams of astronomers made a shocking discovery. They were studying Type Ia supernovae, tremendous explosions that occur when white dwarf stars reach a critical mass. These supernovae have a nearly uniform brightness, making them excellent cosmic distance markers. By measuring how bright these explosions appear to us, astronomers can determine how far away they are. By measuring their redshift, they can determine how fast they are moving away. What these teams found defied expectations. The most distant supernovae were dimmer than they should have been if the universe was slowing down. This meant they were farther away than expected, which could only be explained if the expansion of the universe had been accelerating for the past 5 to 6 billion years. This acceleration posed a profound problem. What force could possibly be pushing galaxies apart faster and faster? It would need to overcome the gravitational pull of all matter in the universe. It would need to permeate all of space, and it would need to exert negative pressure, a concept that seems to defy common sense. Astronomers called this mysterious force dark energy. The name acknowledges both our ignorance, we don't know what it is, and its nature. It is a form of energy that fills space itself. Today, more than 2 decades after its discovery, dark energy remains one of the biggest mysteries in physics. What do we know about dark energy? We know it makes up about 68% of the total energy content of the universe, dwarfing both ordinary matter, which makes up about 5%, and dark matter, which makes up about 27%. We know it causes space to expand at an accelerating rate, and we know it is remarkably uniform, exerting the same influence throughout the observable universe. One possibility is that dark energy is a property of space itself. Empty space, contrary to our intuition, is not nothing. In quantum physics, empty space teems with virtual particles that pop in and out of existence. These quantum fluctuations could create a kind of energy inherent to space, a cosmological constant that Einstein first proposed, then rejected, and that now seems vindicated by observations. If dark energy is a cosmological constant, a fundamental property of space, then as the universe expands and creates more space, it creates more dark energy. This leads to faster expansion, which creates even more space and dark energy, creating a feedback loop of ever-accelerating growth. Another possibility is that dark energy is a new kind of energy field, that permeates all of space, what physicists call quintessence. Unlike a cosmological constant, which remains unchanged as the universe expands, quintessence could vary over time and space. This might explain why the universe expanded rapidly during inflation, then slowed down, and is now accelerating again. Or perhaps dark energy represents a failure of Einstein's theory of general relativity on the largest cosmic scales. Maybe gravity behaves differently over vast distances than our current theories predict. This has led to modified gravity theories that attempt to explain cosmic acceleration without invoking a new form of energy. All of these possibilities remain active areas of research. Astronomers are designing ever more precise observations to distinguish between these models, to determine whether dark energy is constant or changing, uniform or varying across space. Whatever dark energy turns out to be, its discovery has profoundly changed our understanding of cosmic destiny. Before dark energy, cosmologists debated whether the universe would expand forever or eventually collapse. Now, with dark energy driving accelerated expansion, the fate of the universe seems clear: eternal growth. As space stretches faster and faster, galaxies move apart at ever-increasing speeds. Eventually, galaxies outside our local group will be carried away so rapidly that their light can never reach us. They will fade from view, one by one, leaving only our Milky Way and its few closest neighbors visible in the night sky. In the far distant future, perhaps 1 trillion years from now, astronomers in whatever civilizations might exist would look out at a nearly empty universe. They would see no distant galaxies, no evidence of cosmic expansion, no trace of the Big Bang. The clues that led us to our current understanding of the cosmos would have been erased by the very expansion we discovered. This makes our moment in cosmic history special. We live at a time when the evidence of our origins is still visible, when the light of distant galaxies still reaches us, when the cosmic microwave background still whispers to us of the universe's fiery birth. We can still piece together the story of where we came from and where we are going. Dark energy also raises profound philosophical questions. If the expansion of the universe continues to accelerate, then eventually all matter will be spread so thin that stars will no longer form. Existing stars will burn out, black holes will evaporate through Hawking radiation, the universe will become cold, dark, and diffuse, a state cosmologists call the Big Freeze, or the heat death of the universe. Is this the inevitable end of all things? Perhaps not. The history of cosmology teaches us humility. Every time we think we understand the universe, it surprises us. Dark energy itself was a surprise, discovered by astronomers who expected to find the opposite. Perhaps dark energy will change over time, weakening, or even reversing. Perhaps new physics, not yet glimpsed, will alter our cosmic destiny once again. For now, we live in a universe blown gently apart by an invisible force, a universe where space itself grows like a living thing. Each cubic centimeter of empty space contains only a tiny amount of dark energy, equivalent to about 1 hydrogen atom per cubic meter. Yet summed over the vastness of the cosmos, this energy becomes the dominant force shaping our universe's evolution and ultimate fate. As you drift towards sleep, consider the emptiness around you. It is not truly empty. It hums with unseen energy. It stretches imperceptibly. It shapes the grandest structures in the cosmos and determines the destiny of all within it. The void between stars is not nothing. It is perhaps the most important something in all of creation. What does it mean for us, tiny beings on a small planet, orbiting an ordinary star, to exist in a universe that never stops growing? How does cosmic expansion shape our past, our present, and our future? These questions take us beyond physics into the realm of meaning, where science meets philosophy. The expanding universe tells us, first and foremost, that we live in a changing cosmos, with a beginning and perhaps an end. This stands in stark contrast to the static, eternal universe that many believed in before the 20th century. Our universe has a history. It evolves, it transforms over time, and we exist at a particular moment in this cosmic story. That moment, it turns out, is rather special. We live in what some astronomers call the stelliferous era, the age of stars. Before this era, the universe was too hot and dense for stars and galaxies to form. After it, in the distant future, the universe will become too cold and diffuse for new stars to be born. The existing stars will burn out, one by one, leaving a dark, empty cosmos. We also live at a time when the evidence of our cosmic origins is still visible to us. The light from distant galaxies still reaches our telescopes. The cosmic microwave background radiation still fills our sky. The abundances of light elements created in the first minutes after the Big Bang still match the predictions of our theories. But this will not always be the case. As the expansion of the universe accelerates, driven by dark energy, galaxies outside our local group will eventually recede faster than their light can travel toward us. One by one, they will fade from view, like ships sailing over the cosmic horizon. In perhaps 1 trillion years, astronomers in whatever civilizations might exist would look out at a nearly empty universe, with no way to discover how it began or where it is going. This makes our moment in cosmic history privileged in terms of knowledge. We can still see the universe's past. We can still piece together its story. We exist at a time when the universe has cooled enough for complex structures to form, but not so much that the evidence of its birth has been erased by its expansion. The expanding universe also shapes our understanding of cosmic geography. In a static universe, we might imagine traveling far enough to reach some kind of edge or boundary. But in an expanding universe, there is no edge to space itself. The universe might be finite, yet unbounded, like the surface of a sphere, or it might be truly infinite. In either case, there is no center, no special place from which everything else recedes. Every point in space experiences the same expansion. This democratic view of the cosmos echoes the Copernican revolution, which removed Earth from the center of the universe. The expanding universe takes this principle further. There is no center at all. Every galaxy, including our Milky Way, sees other galaxies moving away in exactly the way we do. This cosmic democracy reminds us that our place in the universe is not privileged by location, only by the time in which we exist. The expansion of space also shapes our understanding of the size and age of the observable universe. Because light travels at a finite speed, we can only see objects whose light has had time to reach us since the beginning of the universe. This creates a cosmic horizon, a boundary to our vision. The observable universe is not all that exists, only all that we can see from our vantage point in space and time. And as space expands, this horizon changes. Some galaxies that are currently visible will eventually become invisible as they are carried beyond our cosmic horizon by the accelerating expansion of space. At the same time, light from previously invisible regions might reach us for the first time. Our window on the cosmos shifts as space itself stretches. The expanding universe also gives us a new perspective on time. In a static, eternal universe, time might seem arbitrary or cyclical. But in an expanding universe with a beginning, time has a direction, an arrow. The universe grows larger and less dense. Entropy increases. Complex structures form, evolve, and eventually decay. There is a profound difference between past and future. This cosmic arrow of time aligns with our human experience of time's passage. We remember the past, but not the future. We age in only one direction. We cannot return to earlier states of being. The expanding universe suggests that this one-way flow of time is not merely a human perspective, but a fundamental feature of reality itself. There is also something poignant about living in a universe that grows ever more diffuse. The early universe was a place of intense connection, where everything touched everything else. As space expands, these connections stretch and weaken. Galaxies that were once neighbors drift apart. The cosmos becomes less dense, cooler, lonelier. This cosmic loneliness will deepen in the far future. As expansion accelerates, galaxies outside our local group will disappear from view. Eventually, even the local group will disperse. The Milky Way itself will exhaust its gas for forming new stars. The existing stars will burn out. What remains will be a scattering of stellar remnants, white dwarfs cooling to black dwarfs, neutron stars and black holes. all in a universe too diffuse and dark for new stars to form. Is this the inevitable end? Perhaps not. The history of cosmology teaches us humility. Many times scientists have thought they understood the universe, only to be surprised by new discoveries. Dark energy itself was a surprise, discovered by astronomers who expected to measure the slowing of cosmic expansion, not its acceleration. Perhaps dark energy will change over time. Perhaps new physics awaits discovery. Our cosmic story may have twists we cannot yet imagine. For now, we find ourselves in a universe of remarkable beauty and complexity, made possible by the gentle expansion of space over billions of years. Had the universe expanded too quickly after the Big Bang, matter would have been too diffuse for stars and galaxies to form. Had it expanded too slowly, everything would have collapsed back together before stars could ignite and complex chemistry could emerge. The rate of expansion has been just right for a universe with stars, planets, and the possibility of life. As you rest beneath the night sky, consider that the darkness between stars is not empty, but growing. The void expands, carrying galaxies apart like islands drifting on a cosmic sea. Yet this same expansion has created the conditions for your existence. In a very real sense, you are a child of the expanding universe. The atoms in your body, the energy that moves your thoughts, the time in which you exist, all were shaped by the 14 billion year unfolding of a cosmos that began incredibly hot and dense and has been cooling and expanding ever since. In this way, the cosmic becomes personal. The vast expansion of space connects to your own brief moment in time. You draw breath in a universe of a particular size, density, and age, a universe that will never be exactly the same again. Each moment is unique in cosmic history, and you are here to witness it, to wonder at it, to be part of the universe, becoming aware of itself. As we near the end of our cosmic journey, we face perhaps the most profound question about the expanding universe. Will it ever stop growing? For decades, this question haunted astronomers. The answer seemed to depend on a cosmic tug-of-war between the momentum of expansion and the gravitational pull of all matter in the universe. If the universe contained enough matter, gravity would eventually win this contest, slowing expansion until it stopped completely. The universe would then begin to contract, galaxies rushing toward each other in a great cosmic collapse. This scenario, known as the Big Crunch, would be the mirror image of the Big Bang, with all matter and energy compressed once again into an infinitely dense, hot state, perhaps leading to a new cycle of expansion and contraction. If the universe contained less matter, gravity would slow the expansion but never quite stop it. The universe would expand forever, but at an ever-decreasing rate, approaching but never reaching a standstill. Galaxies would grow increasingly isolated as space stretched between them, but the rate of this isolation would gradually diminish. To determine which scenario awaited our cosmos, astronomers needed to measure two critical values: the rate of expansion and the density of matter in the universe. If the density exceeded a critical threshold, the universe would eventually collapse. If it fell below this threshold, the universe would expand forever. For decades, the evidence suggested we lived in a universe balanced precariously between these possibilities, with just enough matter to slow expansion significantly, quite enough to reverse it. This type of universe, poised between eternal expansion and eventual collapse, was called a critical universe. But as we explored in our previous chapter, this understanding changed dramatically in 1998 with the discovery of dark energy. Far from slowing down, the expansion of the universe is accelerating. Space stretches faster today than it did billions of years ago, and it will stretch even faster billions of years from now. This acceleration fundamentally changes our answer to the question, will the universe ever stop expanding? With dark energy driving accelerated expansion, the evidence now strongly suggests that the universe will expand forever and at an ever-increasing rate. In this scenario, known as the Big Freeze or the heat death of the universe, space will stretch endlessly, growing ever colder and more diffuse. Galaxies outside our local group will eventually recede faster than their light can travel toward us, disappearing from our view one by one. In time, even the galaxies in our local group will exhaust their gas for forming new stars. The existing stars will burn out. Black holes will slowly evaporate through Hawking radiation. Matter itself might eventually decay. The final state of such a universe would be almost unimaginably bleak, an immense, cold void where elementary particles are separated by unthinkable distances, too far apart to ever interact again. Entropy, a measure of disorder, would reach its maximum. No work could be done, no heat could flow, no information could be processed. Time itself would lose meaning in such a static state. This picture of eternal expansion toward heat death currently represents the scientific consensus, based on our best observations and theories. But cosmology has surprised us before, and it may surprise us again. Several alternative scenarios remain possible. Perhaps dark energy will change over time. Unlike the cosmological constant, which remains unchanged as the universe expands, some theories propose a form of dark energy called quintessence that could vary across time and space. If dark energy weakens in the future, expansion might slow again. If it somehow becomes attractive rather than repulsive, expansion could even reverse. Another possibility involves the nature of dark energy itself. If dark energy is not truly constant but grows slightly stronger as the universe expands, it could eventually become so powerful that it tears apart galaxies, solar systems, planets, and even atoms themselves. This scenario, known as the Big Rip, would end the universe not with a whimper, but with a catastrophic tearing of space-time itself. Some theoretical physicists have also proposed more exotic endings. Perhaps our universe exists in a false vacuum state, like water cooled below freezing but not yet turned to ice. A quantum fluctuation could trigger a transition to a true vacuum state, changing the laws of physics throughout the cosmos, in an expanding bubble that would destroy everything in its path. This scenario, called vacuum decay, would erase the universe as we know it in an instant. Or perhaps the universe will not end at all but will continue in cycles of expansion and contraction. While the observed acceleration of expansion seems to rule out a simple Big Crunch, followed by a new Big Bang, more complex cyclic models remain possible. In these scenarios, our three-dimensional universe might be a membrane floating in a higher dimensional space, periodically colliding with other membrane universes to trigger new cycles of expansion. These alternative scenarios remain speculative, but they remind us of the limits of our knowledge. The universe has existed for nearly 14 billion years. We have been studying it with modern scientific methods for only a few centuries. Our theories are based on observations of a tiny fraction of cosmic history. The future may hold surprises we cannot yet imagine. For now, the evidence points to a universe that will expand forever, driven by the mysterious force we call dark energy. This eternal expansion shapes not only the physical fate of the cosmos, but also its meaning. In a universe with no end, no final collapse, no return to its beginning, time stretches on without closure. The story of the cosmos becomes not a tale with a beginning, middle, and end, but an endless unfolding, a perpetual becoming. There is something both troubling and beautiful in this vision of eternal expansion. Troubling because it suggests a universe that grows ever more diffuse, cold, and empty, where structures we cherish, from stars to galaxies to life itself, cannot endure forever. Beautiful because it reminds us that our moment in cosmic history is precious precisely because it is transient. We exist in what might be called a habitable period of cosmic history, after the universe cooled enough for complex structures to form, but before it expands so much that new stars cannot ignite. This period, the stelliferous era, might last for perhaps 100 trillion years. That sounds like an unimaginably long time from a human perspective. But in the context of a universe that expands forever, it is just a brief, luminous interlude in an eternal story. As you drift toward sleep beneath the night sky, consider that you witness the universe during its vibrant youth, when stars still shine and galaxies still form. The cosmos you see tonight is not what it was when it began, nor what it will be in the unimaginably distant future. It is a universe in transition, a moment in a vast unfolding, a universe becoming something new with every passing second. The expansion that carries galaxies apart also creates the conditions for your existence. The cooling that follows expansion allows atoms to bond into molecules, molecules to combine into cells, cells to organize into minds capable of wondering about their place in an ever-growing cosmos. You are not separate from this cosmic unfolding, you are part of it. A brief but conscious expression of a universe becoming aware of itself. Whether the universe expands forever or eventually stops and reverses, whether it ends in ice or fire, or transforms in ways we cannot yet imagine, the fact remains that we are here now, in this moment, in this particular universe of a certain size, density, and age. And that moment, your moment, is unique in the entire history of the cosmos.